I will continue with the Ford and Fulkerson's labeling algorithm that we were that I showed to you last time, and we had obtained an max flow. Sorry, we had obtained a flow of 11 units in a network. So last time I had shown you the augmenting paths, how we obtain through the labeling procedure we obtain augmenting paths, and then once we label T, we know by how much to augment the flow, and also the labels, the second label tells us how to trace back the augmenting path, and so we had managed to obtain this flow. So now we continue some more, and so I'll start with the label here. So this, as we said, is 0 and M for this M, and now you look for example, S1 is a saturated arc. You cannot increase the flow anymore on it. So therefore, I cannot label 1 from here, but 2 still has a scope for increasing the flow on it. So I will label this, and the difference is 1 unit. So I label this as S and 1, right. So that tells us that we can come to 2 from S, and we can augment the flow by 1 unit here. Then we look for the arcs here. So here, for example, this is not used arc at all. The capacity is 3. I can label 1, and so this will be 2, and the corresponding second label would be minimum of 1 and 3, which is 1. So that means I can reach up to 1 from S via a path which has a capacity of 1 unit on it. Okay. Then you can label 3, for example, from here, because you have a capacity of 1 unit left here. So the label here would be 1 and 1. Okay. From 2, I could not have labeled 3 or 6. The idea, I mean, of course, again, as I told you, there is no hard and fast rule how you operate the list that you use for scanning the nodes and then finding out augmenting path. So here from 2, I could not have labeled 3 and 6. I could only label 1, and so then from 1 I can label. I cannot label 4. I can label 3. Now 4-3 is a backward arc. There is no flow on 4-3, so I cannot label 4 from 3. If there was some flow, positive flow from 4 to 3, I could have gone to 4 from 3, right, by reducing the flow. Then 5 is saturated, so that's it. So my labeling algorithm stops here, and I'm not able, because I'm not able to label the node T anymore, right. So so therefore, yes, and I will now prove the Ford and Fulkerson's theorem, that is validity of the algorithm, which says that when Ford and Fulkerson algorithm stops, it stops at the max flow, right. So we need to prove the theorem. So maybe I'll write it out here. Yeah, theorem. So theorem says that when Ford and Fulkerson algorithm stops, it stops at the maximal flow. Okay, so let us prove this. Simple proof. So here, when Ford and Fulkerson algorithm stops, some nodes have been labeled, right. Labeled, and some have not been labeled. Okay, so let us call let W denote the set of labeled nodes, right, and S belongs to W always, because I can always label S, right, and let W bar denote the set of unlabeled nodes. and T belongs to W bar, right. We have stopped because we cannot label T anymore, right. Okay. So, now let us see what is happening. So, if I belongs to W and J belongs to W bar, that means I was labeled and J was not labeled, right. So, this implies, and if Ij belongs to A, that means the arc is from I to J. This implies that Xij, the current flow in the network, is equal to Uij, right. If you have a, remember our labeling procedure was that if you have a forward arc, if you have a arc like this, and that is what we are doing here also, I and J. So, if the flow here Xij is Uij and I is labeled, I cannot label J. That is what was happening here also. I could not label 1 from S because the arc is saturated. So, if I is in W and J is in W bar and Ij is an arc of A, then Xij must be equal to Uij, right. Similarly, for the backward arc, yeah. So, the idea here is, and if I belongs to W and J belongs to W bar and Ji is the arc and Ji belongs to A, right. So, I was labeled and J, so I am saying that here this is your W and this is your W bar, I is here and J is here. So, you have an arc like this. Okay, I should add these two, right. So, this is an arc like this. Now, I is labeled, and if I want to label J, there must be some positive flow on the arc Xji, on the arc Ji, right. So, but I am not able to label J, J belongs to the unlabeled set. So, this implies, so this would imply, this implies that Xji is 0. And now, if you recall the Max-flow min cut theorem, then this, so the cut W bar satisfies the conditions of that theorem, and therefore, the current flow in the network is maximum and the corresponding cut is the minimum cut. So, very simple proof, right. So, what we are saying is that now, so this therefore, the cut W bar and the flow Xij satisfy the max flow min cut theorem. Okay. And this is the complementary slackness conditions as I showed to you, and so many ways of looking at the same theorem. But essentially, it said that if you have a cut and you have a flow such that these conditions are satisfied, that means for I in W, J in W bar, Ij a forward arc, the arc must be saturated, and if I is in W, J is in W bar and Ji is the arc, then Xji must be 0. If these conditions are satisfied by a feasible flow in the network and the corresponding cut W bar, then the cut must be the minimum cut and the flow is maximum, right. And we can now quickly verify the theorem here for this for the flow that we have, because we are not able to proceed any further. Okay. So, what is your cut here? So, the cut W here would be what? We are able to label S 1, 2 and 3, right, and there was the remaining nodes 4, 5, 6 and T. These belong to, so okay, I should not say this is W, this is W bar. Okay, so this is W bar, and now you can see that what are the forward arcs that you have. Say for example, from 1 to 3. So, just check for the arcs. So, your cut, maybe I can just show you that the cut is like this, right? 4, 5, 6 T are in W bar and 1, 2, S1, 2, 3 are in there. So look at all the forward arcs. This 3 to 5 is a forward arc, right? And this is saturated. Then you have 2 to 6. 2 to 6 is a forward arc. This is also saturated, and the arc 4, 3. Arc 4, 3 has no flow on it. So the corresponding X 4, 3 is 0 in the current flow. And so the last arc of this cut is 1, 4. Maybe I can show it this way. 1, 4. You see the cut is this 1, 2, 3, S 1, 2, 3. So this is the cut. So 1, 4. And therefore, now you see that this cut will satisfy the conditions for the max flow min cut, because 1, 4 is also saturated, and you can check for the other arcs also that they satisfy. For example, 4, 3 there is no flow, and all other arcs, the forward arcs, are all saturated. Therefore, this is the min cut, and the corresponding flow is the max flow. So, a very simple basic algorithm, and I showed you that the groundwork for this algorithm was done by the duality theory for linear programming, because I told you that if you look at the restricted dual problem, then it is equivalent to obtaining augmenting path if it exists in the problem in the network for a given flow. Okay. So, a very basic algorithm, but certainly it has many drawbacks, and this was done, let us say 30 years ago almost. So, a lot of improvements have taken place, but let me point out to you some of the drawbacks, and let us see. See, the first thing is the algorithm, because yeah. So, let me make the point here. I will make the point. First point is that how to operate the list for selecting nodes for scanning. Remember how this is a question mark, because nothing is said. You can do it in any way you like. And so, say for example, when you scan a node, that means a node has been labeled, so that is a part of the list. Then you take it out from the list, and then you scan. That means you try to see what are the nodes that you can label from this node, and then you put the labels and you add them to the list. So now you may operate a list like this. Like for example, you take a node 2 and then you try to label 3 or 4. So you will add. So there may already be some nodes here. So you will put 3 and 4 here, or you may decide to put 3 and 4 on top, or maybe somewhere in between. And then when you want to pick up a node from the list to this thing, then you may either take this one, or you may take this one, or you may choose a node at random. So there is no hard and fast rule given in the Forden-Wilkerson's algorithm to how to operate the list, how to pick a node from the list, right? So therefore, I want to show you what can happen. Say for example, a pathological case I am showing you. So what will happen here? Look at this network. So here the capacities for these 6 arcs is for each of them is 10,000, and for arc 1, 4 and 2, 3 the capacities are only 1 unit, right? Now it is possible I may choose my augmenting path. So I may choose the augmenting path. I may choose the augmenting path S1, 4 and T. Now nobody stops me, because from S I will be able to label this node and this node, right? So this would be 10,000. I mean this will be S and 10,000. Then this will also be S and 10,000. Okay. And then I may decide to pick up one. So both these nodes get added to the list. Then I pick up node 1, and from here I can label this as 1 and 10,000 okay, and I will label 4 as 1 and 1, right? And then now I may decide to choose 4 from, I must decide to pick up node 4 from the list, because 3 and 4 will both get added to the list. So, once I pick up 4, then I will be able to label T, and the label to T would be 4 and 1. Yes. So, and the moment I label T, I stop, because I have labeled T, and so I have found an augmenting path, and so this will be an augmenting path, and the flow will be for 1 unit, right. Now, in the next and so then again you erase the labels, because that is what the algorithm says, that once you have found an augmenting path, you erase all the labels and start all over again. So, when I do it all over again, so right now my flow is this direction, this and this, right, and 1 unit of flow. Now, in the next iteration, I start labeling, and let us say I label 2, I can again label 1 and 2, then I pick up 2 from the list, and 2 I will label 3 and 4, right. So, I will go this way and this way. Then from 4, I may decide to label 1, because there is a 1 unit positive flow on the arc 1 4, I can label 1 from 4. So, I will go this way, then go this way, and then this way. So, that means the next augmenting path that I will choose would be S 2 4 1 3 and T, and this also has capacity 1, and I may, nobody stops me from repeating this, choosing this augmenting path, because once I have done this, then I can again choose S1 4T as an augmenting path, right. Remember, because these are enough capacities here, because I have now removed the flow in this direction. So, therefore, I can again label 1 to 4, right. I will do it this way and then go to T. So, this I will then end up repeating 10,000 times, but if I were to simply choose the augmenting paths S1 3 T, then this has a capacity of 10,000, and this will be S2 4 T, which will also have a capacity of 10,000. So, in 2, if I just my choice of 2 augmenting paths, and I would have got the max flow, which is 20,000. So, therefore, a lot depends on how you operate the list, which has not been spelled out in Ford and Parkinson's algorithm. So, this is what the latter algorithms, they try to give a lot of improvements, and now we have very efficient algorithms. So, yes, here probably I think I would just like you to sit down yourself and work out as to how you can get 20,000 flow by doing alternatively using this as an augmenting path, this as an augmenting path, and then reversing the flow, and you should be able to obtain it. Okay. So, this is one. So, how to operate the list is the ambiguity is there in the algorithm, and that can play havoc with the algorithm, because you cannot. Okay. Now, second thing is, even though I showed you that the basis for the algorithm is from the primal dual algorithm, we are not working with basic feasible solutions, because at every iteration I am augmenting the flow, and so therefore, we are no longer actually using the primal dual algorithm, because the way we go on augmenting the flow, we lose the basic feasible solution of the character of the basic feasible solution, right. So, therefore, finiteness is in danger. So, let me, or one cannot guarantee. So, no guarantee for finiteness of the algorithm. Okay. Now, of course, if all if the uij's are all integers, then every augmenting path will have integer capacity, right. If all, so integer capacity. Therefore, the number of iterations, because you will at least augment the flow by 1 unit at every iteration if you have uij's are all integers. So, therefore, the number of iterations it will be where V bar is the max flow in the network, is the max flow. Okay, so I hope it's clear, because at every augmenting path the flow must increase by 1 unit, and so you go on adding, and since this is the max flow, you cannot have more than so many iterations, and the amount of work that you do at each iteration is because you scan all the arcs. So, the idea is that you do not do more than order m work or order n square. Well, that is not really so important, but the algorithm is finite, right. Now, if the capacities, if some uij's or if the uij's are rational numbers, see, then I can multiply, I can change, if the uij's are all rational numbers, multiply the uij's by the LCM D of the capacities, right, of the capacities. LCM by the LCM of the denominators, by the LCM of the denominators of the capacities. Right. So, and then if you multiply by the LCM, then all the capacities, the new capacities will become integers, and so again the flow will be, the number of iterations will be finite, because you have integer capacities. That means it will be something like d into V. If V bar is again the flow, V bar is the flow, and since you have multiplied the capacities by d, so therefore this will be the total flow in the current network. So, again the number will be finite, and I can then, to get the original flow, I can scale it by the number d and get the, right. So, this is fine, but if the capacities are not rational numbers, they are real numbers, irrational numbers, which again is only normally in physical life you are not going to have capacities as irrational numbers, and therefore that is only for the sake of mathematical completeness, that in case some of the capacities are irrational numbers, then your algorithm, and Ford and Fulkerson actually worked out an example, and they showed that if the capacities are irrationals, then the algorithm will not terminate, because your augmentations may be, remember, an irrational number can be written as a infinite decimal. So, therefore, the increments may be such that they will never add up to the total number. So, the algorithm will not terminate, right, but that is again just for the sake of completeness, that you want to discuss the case of irrational capacities. But in any case, even this is not a very good bound on the number of iterations, because you can improve on the, and okay. So, third thing is the wastefulness of the algorithm, right. So, yeah, this was number 2, this was our number 2, and now let me talk of the, you saw yourself here, maybe I will just, yeah. So, third point is wastefulness of the labeling procedure. Labeling procedure. See, yourself saw that, maybe I can just repeat this here again. What we are saying is that, see, the algorithm says that once you have found an augmenting path, you can just begin again afresh and drop all the labels. But see, for example, here as we saw, we could label this as S and 10,000, okay, and here also I could label S and 10,000. Then depending on, okay, suppose I choose this one, then the label would be 2 and 1, right, and here the label would be 2 and 10,000. Okay, and then again if I choose 3 for example, then the label would be for T would be 3 and 1, right. So, once I have labeled T, I will just say that I can augment the flow along the path S 2, 3 and T, because I have come to T from 3, I came to 2, 3 I came from 2, so 2 here, and 2 I came from S. So, this is my augmenting path. I augment the flow by 1 unit, and so the algorithm says erase all the labels, but you see here if I do not erase, then I can also find some other augmenting paths. For example, this I can find here, right, S1 3T or S1 4T. There are 2 more augmenting paths that are available, but I will not find them right now, because the algorithm tells me to go back, erase the labels and start again. So, this is where people like Edmonds and Dinnick, the references would be available in the textbooks that I have given you. So, these people tried to improve on it. So, they tried to improve the how to operate the list, and then not you try to find as many augmenting paths as possible in one go, right. Just do not find one augmenting path at a time, and that requires some extra knowledge of how you search network, and these are how you search a data list, and there are things like depth search, depth first and breadth first and so on. So, breadth first searches will give you more than one augmenting path at a time, and therefore, you can really increase the flow along all these paths simultaneously and then work out. So, therefore, your effort of labeling will be used to a greater extent, because the labeling that you have done, you will be able to find more than one augmenting path. So, this is the idea behind it. So, therefore, this is all that I want to comment about the labeling algorithm, right. Okay. And as I said that we are talking of linear programming and its extensions. So, therefore, the scope of the course does not really allow us to talk about the various improvements in the algorithm here. So, let us do some post-optimality analysis here also, as usual, because the data can keep changing, and so you should be able to update your solutions according to the changes. So, here let me start by some definitions. So, what we are saying is that suppose let me denote this V psi, or okay, not V psi, I want to use V psi as the equal to flow in the network when capacity of arc ij is equal to psi. That is, I am saying that I am considering the case when uij is equal to psi. So, this is my notation, that V psi is the flow in the network when capacity of arc ij is psi. Okay. Now, let us see here. Let me define u1 as the set of all cuts in which ij is a forward arc. Yeah, so that means every cut here will have I in the first set and j in the second set, right. So, this is a collection of all cuts in the in which ij is a forward arc, right. And let us define u2 as the set of all cuts in which ij is not a forward arc. Okay. That means, if you have a cut here, and so either in this case either I and j both are here, right, or ij are here. So, they are not it is not occurring, or it can be ij is not a forward arc. So, it means that I is here and j is here, then this is an arc. So, this covers 3 cases, and the forward case was that only this is the thing, that is I is here and j is here. So, then it is a forward arc. If it is not a forward arc, then we are looking at this thing, right. So, now you see that here, yeah, and now let me define, let C1 be the capacity of the minimum cut in U1, yes, and C2 is the capacity of the minimum cut in U2. Not that I am saying that we really have to find it, I am just denoting, because this is a finite set of cuts, and so among all these cuts we compute the capacity and select the one for which is the minimum capacity, and we say that that capacity is equal to C1. Similarly, this is C2 here, right. Now, see for so it's like this, if yeah, and this okay, set of all cuts, capacity of the minimum cut in U1 when psi is 0. So, I am just putting the capacity of the arc ij as 0 and then finding out the cut with minimum capacity. So, now when yeah, so when uij is equal to psi, flow or okay, not flow, capacity of all the cuts in U1 will go up by psi units. Yeah, it should not look at all complicated, because as we said that since I is here and j is here, so this is a forward arc. C1 was computed as the capacity of a minimum cut when psi was 0. Now, if I increase the capacity of this arc, then the flow will go up by psi units, right, because remember this is all the cuts, the capacity will go up by psi units. So, the minimum capacity will also go up by psi units, right. And so, now we say that the flow, the max flow in the network, and therefore, max flow is equal to minimum of C1 plus psi and C2. Remember your max flow min cut theorem. So, if C2 is the smallest number, then smaller than this, then this will be the max flow, and if so, here this is this. So, now if C1 is greater than C2, this implies that C1 plus psi, because psi we are taking to be non-negative, either psi is 0 or positive. This implies that C1 plus psi is greater than C2. Yeah. Therefore, C2 is the max flow. Right. And if otherwise, what do we get? Psi, if it is less than C2 minus C1, you see, if psi is less than C2 minus C1, then psi plus C1 will be less than C2. Okay. And so, yes, so therefore, psi less than this will imply that C1 plus psi is less than C2, less than or equal. So, therefore, the cut in U1 will remain min cut for psi greater than or equal to C2 minus C1. So, this gives you a good idea, and therefore, that means one would have to solve to get this number, one would have to solve two max flow problems, one with psi equal to 0 and with the other one. So, when you obtain when you want to obtain the value C2 here, okay, let me just define. Yeah, so to obtain C2, what we will do is we will put the capacity of arc ij as infinity, very large number, so that it never occurs as a forward arc in a flow in a mid cut, right. And so, that means you can compute the max flow for psi equal to 0 and for psi equal to infinity. You get the number C1 and C2, and that tells you psi is this, right. So, here that means, and so we say that it's the capacity or the critical capacity of arc ij is equal to C2 minus C1, which is V infinity minus V 0. That is another notation, right. That means, see, it was V psi. I started with the notation V psi. So, V infinity means that when you have made the capacity of arc ij very large, and this is when you have made the capacity of arc this. So, now or 0, right. So, the critical capacity, and then the question is, so that means what would be the loss in the max flow. So, this you can also call as K star ij. We call it the critical capacity, right. So, loss in the max flow is equal to minimum of Uij and Kij star, whichever is the small, right. If psi is less than this, then of course, this will be the, that means if Uij is less than Kij star, then this is the critical capacity. The loss in the max flow would be this. If Uij is greater than Kij star, then the loss in the max flow would be Kij star. So, this is what the idea, and so it has a very interesting application that, for example, when you, in the time of war, if the enemy wants to destroy some supply line to the enemy's this thing, they would want to know which will give the maximum damage. That means, they want to stop the supplies reaching the camps of the enemy enemies. So, therefore, they would want to know which one they should strike, so that they get maximum, they do maximum damage. And there are many other, or for example, you may want to improve a certain route. So, then you want to know that which is a very the question is of finding the most vital arc in the network, and the most vital arc will tell you. So, for example, for arc ij, I know that this is the amount by which maximum flow will be lost in the network. So, then I can do this exercise for each arc, and then try to find out which is the arc which we gets destroyed, then there will be maximum loss to the max flow in the network, and many more interesting exercises we will do with this. So, I will try to show you some more applications of the max flow problem in the next lecture. Let us consider this example, and I will try to explain all these concepts that we have discussed. So, here you see currently there is a 12 units of flow in the network. Make sure that there is flow conservation at each node. So, 9 units are going on arc 1 2 and 3 units on 1 3. Then these 3 units are diverted on arc 3 5. Right, and then this 9 units, 6 of them come on arc 2 5, 3 go from 2 to 4. So, this 6 plus 3 9 finally go from 5 to 6, and this 3 units go from 4 to 6. So, the current flow, total flow in the network from 1 to 6 is 12 units. Okay. Then you see that the capacity of arc 3 4 is a function of lambda, and so your max flow will also be a function of lambda, right. Now, let us try to look at all the cuts in which arc 3 4 figures as a forward arc, and just to explain to you the concept of cut and you become familiar with it, I have just written down all the cuts, all possible cuts. This is a small example. So, you see in all these cuts 3 and 4 are on different sets. So, therefore, these cuts separate nodes 3 and 4. So, here and then you write down the capacities of each of these cuts, and it turns out that the cut 1 2 3 4 5 6 is the minimum cut among all these cuts. So, therefore, C1 equal to 12 is the flow in the network when you treat the capacity of arc 3 4 as 0, right. And as the capacity of arc 3 4 will go up, it is from 2 plus lambda. So, from 0 to it becomes more and more positive, then the flow the total flow from 1 to 6 also will go up till, as we said. So, now if you consider the cuts in which 3 4 does not figure as a forward arc, in that case these are the possible cuts 1 2 3 4 5. Again we write down the capacities, and this will turn out to be the min cut, and the capacity of this cut is 17. Okay. So, therefore, now you want to know how far the capacity of arc 3 4 can be increased, so that the cut 1 2 3 4 5 6 remains the min cut, and for that you will want to say that 12 plus 2 plus lambda, because the capacity of arc 3 4 is 2 plus lambda. So, this total number should be less than or equal to 17. So, as long as your lambda, and so this implies lambda is less than or equal to 3, and here lambda can be as low as -2. So, as long as lambda is between -2 and 3, the flow, the cut 1 2 3 4 5 6 will remain the min cut, right. And the moment lambda is equal to 3, then your capacity of arc u 3 4 will become 5, right, and the flow in the network can be updated. So, let us just see how you can update the flow in the network. So, that is what I am trying to show you here. So, we will do the labeling algorithm, right. We will start with 0 m here, and if you want to label, right. So, you will label node 2. Say for example, this is I am showing you the addition of the flow, but here currently 20 is the capacity, 9 is the flow. So, therefore, I can label node 2 as 1 11, right, the difference. That means 11 more units can come from 1 to 2, right. And similarly, for node 3, current flow is 3. So, the first number indicates the node from which you are coming, and then 2 is the additional flow that you can have on arc 1 3, right. And then see from 3, from 2 you cannot label these two, right. So, again as you saw that in the Forden-Fulkerson algorithm, there is no hard and fast rule how you operate the list. So, for example, from here I can try to label 4. So, from 3, therefore, the first label is 3 2. So, because this number is 2, so I can at most flow to 2 more units on 3 4, and therefore, the label is 3 2, right. And once you have this, then if I decide to scan this node, then you will have 2 more additional units of flow going from 4 to 6, and so the total flow will go up to 14 units, right. So, 4 2, this is the final this thing. So, initially your flow in the network was 12 units, so 2 more units, right. And so, this becomes saturated now. Now, again if you want to label you start labeling from node 1, then what is happening? Okay, so this is 3 plus 2 as we said. So, this gets so there's I cannot label 3 from 1, but I can label 2 from 1, and again the flow the label is 1 11, right, because still the flow here is 9 units, right. Then from 2 you can label 3, right, because the capacity of this arc is 4 units. So, therefore, the label would be 2 4, and these two nodes I cannot label from here, but from 3 I can again label node 4, because I have used only 2 units of flow here. So, 3 more, I should have said 2 plus 3. So, because right now I had 2 units of flow going from 3 to 4. So, now 3 more units can go. So, therefore, the label for 4 is 3 2, right. 2 more units are coming. Okay. What is happening? Why am I having 3 plus 2? This should be 2 units. Right. Now, I have 3 units coming here from here, right. And so, 3 units more are going on 3 to 4. So, the label is 3 3. From this thing, right. And so, you have additional unit of flow 3 units from 4 to 6, right, because from 3 I cannot label 5, I can only label 4. So, 3 more units. So, 5 more units in the network, and therefore, the total flow is now of 17 units. The label for 6 is 4 3, because from 4 you could come to 6 and you could add the flow up to 3 units, right. So, this is the updating of the flow when your capacity of the arc 3 4, that means when lambda is 3, then the capacity of arc 3 4 is 5 units, right. And this is what we found out from here also, and the capacity, and therefore, by the now when for lambda greater than 3, if you want to label, for you want to see if how far your labeling algorithm will go. So, then again this arc has extra capacity because this is only 12. So, here the label would be 1 8, right, because 12 units of flow. Then from here the label would be 2 1, because you have 1 unit of capacity left here, and since lambda is greater than 3. So, you will have some extra capacity here, whatever it is. So, it will be lambda minus 3, right, lambda greater than 3, because I am considering the case lambda greater than 3. So, here the label would be 3 and a minimum of 1 and lambda minus 3. Okay, I am treating the capacities as integers. So, therefore, it will be 1 at most, yeah, because if lambda is 5 or 6, even then this will be only 1, the minimum, right. And then you cannot label anything from here, right. There is no flow on arc 5 4. So, I cannot label 5 from 4, and this one is saturated. So, that is it. So, therefore, your labeling algorithm will stop here, right, and you would have been able to label the nodes 1 2 3 4. Therefore, by the labeling algorithm, your cut now is 1 2 3 4 comma 5 6, and this must be the minimum cut, because I am not able to increase the flow anymore. And the critical capacity of arc 3 4, which we talked about a few minutes ago, denoted by k star 3 4, which is the difference of the flow, max flow when lambda is infinity, minus the max flow when lambda is minus 2, right. So, this is 17 minus 12, which is 5, and therefore, the loss to the max flow would be the minimum of these two numbers when lambda is between minus 2 and 3, but when lambda is greater than or equal to 3, the loss in the network will be 5 units. So, it would not help if you increase the capacity of arc 3 4 any further, because the max flow will not increase. Right. So, this gives you an idea how much to invest on a particular route and so on, and as I told you, so many other applications of this concept of critical capacity of an arc. So, now you would want to find out the most vital arc. That means, destroying an arc the most vital arc will be that arc destroying which you will give maximum loss to the max flow. And therefore, as I was mentioning earlier, in war times you want to if you have to destroy more than one supply chain, then you would want to know which is the chain which will cause the most damage. That means, you cannot, the supplies cannot be, the maximum amount of supplies cannot be reached to the enemy camp. That is the idea. So, the concept of most vital arc will come through here, right. And as I had mentioned earlier also, that you would end up solving, if you want to find the most vital arc, you will end up solving 2 max flow problems for each arc, one with capacity 0 and the other with capacity infinity, and then out of those max flows, the 2 n max flows that you get, or the number of arcs, you will have to do it. So, if m is the number of arcs, 2 m max flows you will be solving, and then from there you will compute the most vital arc. So, remember when we were talking of the bounded transportation problem and the min cost flow problem, I had told you that how to obtain a starting feasible solution I will discuss once I had introduced the concept of max flow, and this is what I want to come back to here. So, here the idea, see, this is just I have drawn without showing you the cost, because they are not needed here, we will not be using them, it is only the capacities that you would be requiring. So, and so on, you can just fill up the other numbers. So, the idea here is that this is a min cost flow problem and the BIs add up to 0. So, the negative ones, that means the demand things I have denoted by less than 0, the others are all positive. So, the idea here is that you add a super source and then connect the nodes which have positive supply available at those nodes, and so here then I will make the capacity of this arc as B1. Similarly, this is positive, so I will add another arc here, and the capacity of this arc will be B3, and then you have B4. So, I will have to add an arc like this, and the capacity of this arc will be B4. Fine. And then for the demand nodes, I will add a super source T, super sink T, okay, and then connect B2 is okay, so I will have to draw it this way, right, and the capacity here will be minus B2, remember, because this is negative. So, I need this capacity to be positive. Then you have B5, so this will be like this, and the capacity here will be B5, and finally, this is minus B7. So, you see that this is now a max flow problem, because I am ignoring the costs here, or the capacities as given to you in this arcs. For the new arcs that I have added, I have defined the capacities. So, now you want to solve this as a max flow problem. Okay. And you can see that immediately if the max flow comes out to be, see for example, here the cut, because remember you want all the supplies to be used up, then only, and once you use up all the supplies, because sigma B I is 0, all the demands will also be met, and so that will be a feasible flow in the network, right. Solve this as a max flow problem. If the max flow is equal to summation B I, so I summation over I, such that B I is greater than 0, feasible flow has been found. Feasible flow has been found. Okay. And you can see that the cut will either be this, or a cut will be this, and both these cuts have the same capacity, which is equal to either sum of the B I's, B I positive, or sum of B I's, B I's less than 0. So, once you have a feasible flow, that is okay, because you do not need in the min cost flow problem we were working, remember, for the min cost flow problem you required a solution in this form, where this was the tree, spanning tree, then arcs at their lower bounds and arcs at their upper bounds. So, it is not necessary that when you solve the max flow problem you will get it in this form, but then you know how to reduce any feasible flow to this form by if you have flow along cycles, you can drop one of the arcs and then try to. So, we know enough of the simplex network simplex algorithm to be able to reduce a feasible flow to this form. So, you can do it, and now there is no difference between the min cost flow problem and the bounded transportation problem, except that the underlying network for the bounded transportation problem is bipartite, right. You have this set of, so you are the supply points, these are demand points. So, then it is simple, you will be adding arcs like this, and of course, these arcs are already there, then you will be adding arcs like this with the required capacities, whatever is demanded at these nodes, right. And so, again you can solve a max flow problem, and here also you will not get a basic feasible solution, because you will have to work with a basis of size m plus n minus 1 arcs. So, then you again you know how to using theta loops you can reduce it to a basic feasible solution, where some of the arcs will have to be at the upper bounds, but non basic structure, right. So, this was the idea that using of course, I gave you ad hoc methods for finding out optimal solution, starting basic feasible solutions and so on for min cost and for transportation problem, bounded transportation problem, but this is a neat way, because you can just program the problem, and the max flow algorithm, which now we have very efficient max flow algorithms, will help you to find a starting feasible flow, and then you can reduce it to a basic feasible flow the way you want it for working with the algorithm further on. That is what I had told you I will come back to when I have introduced the concept of max flow. So, I will discuss assignment 8 today, which is based on your shortest path and max flow problems. So, in the first problem I have asked you to find a maximum capacity path. So, capacity of maximum capacity path from node I to node j I am definingCijm. So, this is trying to modify the Floyd-Warshall algorithm, which was finding out the shortest path between every pair of nodes. Now, I want you to find out between every pair of nodes a path which has maximum capacity. And remember, the capacity of a path is the minimum of the capacities of its arcs. So that means it's a double edged problem, in the sense that you want to find a path whose capacity is maximum, and the capacity of a path is the minimum of its arcs which make up the path. So this is what, and therefore the recursive equation is a simple modification of the Floyd-Warshall equation. So here you will be choosing maximum ofCijm, where of courseCijm, as we said, is the maximum capacity of a path from node I to node j, when only nodes 1 to m minus 1 are used, exactly the same way as we defined for the Floyd-Warshall algorithm, but here we are talking of the capacity. So up to m minus 1 nodes have been used. So now when you want to include the node m, you will compare the two valuesCijm, which is not including node m, and then you see when you include the node m, you have Cimm and Cmjm. So the minimum of the two, because whichever arc you use, you will have to say that the capacity will only increase by the minimum of the arcs that you are adding to the path, and so and then you will choose the max, because if you have choice for example, this is Im and Mj, yeah, okay. So this will be Cij m plus 1 will be max of Cijm and minimum of Cimm comma Cmjm. So this we will use repeatedly, and then finally for a node, for a network with n nodes, you will have to compute Cij n plus 1. So here I have asked you to now apply this recursive method to find out the maximum capacity path between every pair of nodes for the given network. So this is your problem 1. Okay, let's go to problem 2. See, problem 2, I am asking you, I have given you this matrix of distances between nodes, right. So that means the entry ij entry of this matrix will give you the length of the arc from I to j, node I to node j, and I am asking you to find the longest path. I want you to solve the longest path problem here from node 1 to all other nodes. Okay, and I have discussed this with you of how to apply the shortest path algorithm here. That means you will replace the Cij's by the minusCij's, and then solve for the shortest path, and then those paths will correspond to the maximum path. So this is your problem 2, right. Now problem 3, I have given you network, and the first number gives you the capacity, and the circle numbers give you the flow on the arc. So here conservation of flow is maintained. I have checked it, and you should also find out that the conservation equations are satisfied. Then I just so that you get familiar with the cuts and their capacities and so on, I have asked you to specify 2 ST cuts, one cut with arc 6,5 as a forward arc. So find out an cut which has 6,5 as a forward arc. Then compute net flow across these cuts. Remember, I defined this term for you, and verify that it is equal to the flow in the network. So the current flow in the network is 20 units. So you have to, whatever 2 cuts you find out, you will have to find out the flow, net flow across these cuts, and then show that for both the cuts the value is 20. Okay. Then in the second part, I want you to find out 2 augmenting paths and augment the flow along them. Okay. So this is problem 3. Now problem 4, I have, because we did not discuss this in the lecture, so I thought through the assignment sheet I will familiarize you with the situation when you have node capacities also. So you have arc capacities, that means you have the limitation on the amount of flow that an arc can handle, but suppose you also have limitation on the amount of flow that a node can handle, because your warehousing thing may not be, the capacity may be limited and so on. There are many situations which you can formulate with the node capacities also. So now here, for example, if node I has a capacity of UI units, the amount of flow it can handle, then I am saying that you transform this, you split the node into 2 nodes I1 and I2. So the incoming arcs to node I1 will now be incoming to I1. Then I join, oh, the arrow should have been there, I1, I2, there is an arrow. This arc has a capacity UI units, and then the outgoing arcs from node I will be now outgoing from I2. Okay. So, you see that because the arc I1 I2 has a capacity ui, therefore, neither the node I1 nor the node I2 can handle a flow of more than ui units. So, I take care of the situation that node I cannot handle more than ui units by doing this transformation. And once you do this, you have been able to transform the node capacity problem to the usual max flow problem, in which the only the arc capacities are required to be satisfied. Okay. So, this is your problem 4, and then I have asked you to solve this problem. I have given you a network flow. So, convert this to a regular max flow problem. Okay. And I have mentioned that the nodes 6, S, 6 and T do not have any node capacities. That means they have infinite node capacities. So, that is your problem 4. Now, problem 5. Okay, I'll have to yeah. So, problem 5, when you have presence of undirected arcs. Okay, then it's possible that some arcs you have not specified the direction in which they can be used. So, the idea here is that you replace the arc ij, which is undirected and has capacity of uij units. You replace it by two directed arcs ij and ji, and make the capacities of both the arcs as uij equal to uji, which is given to you. Then you solve the max flow problem, and if xij minus xji is greater than 0, that is in the optimal flow, xij is your vector of flow, then if xij is greater than xji, then that means you will be using the flow, the vector, the arc in the direction I to j, and if so, therefore, we will replace the edge ij with the arc ij, and if xij is less than xji, then we will be using the arc in the backward direction, or that means that the edge ij will be replaced by the arc ji and with capacity uij. So, solving a max flow problem will tell you, because this again in a traffic situation, you see the people who want to avoid rushes and traffic jams, they may want to know which will be profitable. So, they want to see that the max flow would be possible by using the street or the road in a particular direction, and this will help them to determine the direction in which they should allow. So, they will make it one way and they will allow the traffic in the direction in which you have the max flow possible in the network. Okay. So, this is a situation we are trying to model here, and yes, and so so now this is your diagram I have drawn for you. Arcs 3, 5 and 2, 4 are undirected, and so you have to replace them by two directed arcs, solve the max flow problem, and then find out which is the best direction to give to these two arcs. So, now here I have referred to these 3 books which I have been referring to even earlier, but there are a lot of problems in these 3 books on the topics of shortest path and max flow, and lot of applications. But of course, all these 3 books are good for trying out your problems on whatever material we are discussing here. So, they should take care of your topics, shortest path and max flow.